The principle of conservation of energy states that energy cannot be destroyed or created, and it can only be transformed from one form to another. In this example, where an object is dropped from a certain height, let's denote it by h, and the mass of the object by m, then the potential energy of the object would be equals to U equals to mgh, where g is the gravitational acceleration and m is the mass of the object. And this quantity is going to be a conserved quantity. So at the moment, because the object is stationary, so the kinetic energy, which is represented by this expression half mv square, is equal to 0 when it's at the top position. And when the object is dropped and fall onto the ground, then what happens is that this mgh is going to be equals to half mv square. Yeah, so and from here we can roughly estimate that v is going to be square root of 2gh. And the reason why I say that this is only an approximated value is because we made an assumption that there's no loss to the air friction. So what happens is that in the process of falling down, there will be air friction which come into the picture, and that actually cause the loss of energy to increase the temperature of the air. Alright, so in part B, a helicopter takes off vertically. It starts from rest at time t equals to 0 and has a constant upwards acceleration of 0.4 meter per second. So, and then the mass of the helicopter is given as 14,000 kilogram, and g, which is the gravitational acceleration, as usual, is given by 10 meter per second square. Alright, so in the first part we need to calculate the speed of the helicopter at time t equals to 20 seconds. So we have this equation which describes the velocity of the helicopter at time equals to t, and this expression is given by v0 plus at, where a is the acceleration of the helicopter and v0 is the initial velocity when time equals to 0. And in this case here, it's stated that it starts from rest at time equals to 0. So so from there we know that v0 is equal to 0. So at v t equals to 20, then this is simply equals to 20a. And since we know that a is equals to 0.4, then this is nothing more than 8 meter per second. And for part 2, we need to determine the resultant force acting on the helicopter as it rises. So let's represent the helicopter by this object here. So basically there are two components of forces acting on the helicopter. One is the force of lifting, which accelerate the helicopter upwards, and the other one is the gravitational pull. So, and let's represent this unit by F and the other one by mg. Alright, so the resultant force would be given by the lifting force minus of the weight of the helicopter and then this resultant force is going to give rise to the acceleration of the helicopter, which is m multiplied by a. So basically to get the answer to these questions, we just need this information, and of course the acceleration of the helicopter, and luckily it's already given in the questions. So this is just equals to 14,000 multiplied by 0.4, and the answer would be 5,600 Newton. Alright, so for part 3, we need to determine the upward force, which is this one here, on the helicopter as it rises. So what we need to do is just to rearrange the equation such that F is equals to m multiplied by a plus g, and since we know that a is 0.4 and m is 14,000, then we just substitute the value into the equation. So this is equals to 145,600 Newton. Alright, this is the answer for the first choice of question number 11. Alright, let's look at the alternate option. So it's about Brownian motion. So part A, Brownian motion provides evidence that the molecules in a gas are moving. So part 1, draw a label diagram of an experiment that demonstrates Brownian motion. Alright, so this diagram, actually there are more than one experiment with which demonstrate Brownian motion, and in this example here I'm just going to draw a simple one which consists of a smoke cell which contains smoke particle, and of course to observe the motion of the smoke particle we need to use an microscope. So this is just a microscope, and then what we see from the microscope would be the so-called the motion of the small particle from one position to another through some zigzag trajectory, which we call it as Brownian motion. Alright, so this we need to describe what is seen and explain how this shows that molecules are moving. So from here we can actually see that the particle is going through a random walk, which indicates a collision. There are some kind of collision between the smoke particles, collision between the smoke particles and the air molecules. Yeah, and that's the reason why we can see, there's a sharp turns and this kind of like random walk behavior. Alright, and for part B, so in part B, there's a diagram showing that there's a piston which push again the air that trapped in between the space of the piston and the cylinder. So it's given that the cross-sectional area of the piston is equals to 4.0 multiplied by 10 to the power minus 4 meter square, and then the pressure of the gas is given as 1.5 times 10 to the power 5 Pascal, and then atmospheric pressure, let me represent it by PATM, is equals to, of course, 1.0 times 10 to the power 5 Pascal. Alright, so from here we need to determine the mass of the piston when the entire system is in equilibrium. So before we solve the questions, let's examine what's the component of force that acts onto the piston. So at first, there will be the gravitational pull, which is due to the mass of the piston itself, and then um, there's an additional force which is given by the air pressure from the outside, which is caused by the atmospheric pressure, and then the force which go against the gravitational pull is the pressure which provided by the air trapped within the cylinder, and let's call it F1, and then this is F2, and then this the third component which is due to the mass of the piston is simply mg. So if we write out the force equation, then F1 is the force component which point upwards, must be equals to the sum of the force component which point downwards. So F1 will be equals to F2 plus mg, and then our goal is to calculate the value for the mass of the piston, which is m. So what exactly is F1? So F1 is given by the pressure multiplied by the cross-sectional area of the piston. So F1 is just equals to P multiplied by A. Alright, and then for F2, it's the same. It's a same idea where the pressure is given by the atmospheric pressure. So it's PATM multiplied by the cross-sectional area of the piston. Yep. So from here we can rearrange the equation in such a way that m is on the left hand side of the equation, and then we move the g over to the other side as well, and then this would be our cross-sectional area of the piston, and then we have P minus PATM, right? Yeah, I mean it's nothing more than of course I skip a step, which is to move the F2 over to the other side of the equation, right? So from here, because F1 is minus because of F1 minus F2, so we have a minus sign for the atmospheric pressure. So by just substituting the number into the equation, we get m equals to 2 kilogram. Alright, and then part 2, we need to explain how these extremely small molecules in the gas are able to support the weight of the piston. So the idea is that because we know that there are air molecules in the chamber trapped in between the piston and the cylinder, and we know that the air molecules have certain has a certain level of kinetic energy, and when there's an impact in between the air molecules and the piston, there will be transfer of momentum from the air molecules onto the piston. So when the entire system is in equilibrium, where the piston is no longer moving downwards, we can say that the rate of the momentum transfer from the air particle, or we call it air molecules, to the piston is the same as the weight of the piston, which is mg. Yeah, so I repeat the answer again. So the rate of the momentum transfer due to the molecules impact is the same as the weight of the piston, and that's the condition for the equilibrium. All right.